Okay, so now I simply invite the chair of this first journey, Roberto Gilli, to introduce the topic of today and the 2 nights. So Roberto, please.
Okay, thanks, Paolo. So hello, everybody. Thank you for joining the AGN Tourneys this year. So it's a pleasure for me to be the chair of the first tourney of this week. It will be on high redshift quasars, so formation and the evolution of the first supermassive black holes in the universe. And the 2 opponents, or rather the 2 speakers, are Roberto Decarli and Marta Volonteri. So Roberto will start. He will talk about 20 minutes, then Marta will follow, again 20 minutes, and then we will have about 20 minutes of question time combined. I think neither Roberto nor Marta need very much of introduction, but just briefly, let me just say that Roberto is a very well-known expert in observation of high redshift quasars. He has done seminal work on arm observations of quasars at redshift 6 and beyond, and their companion. He's involved in wide area surveys for the search of the most distant AGN. He's also now exploiting arm observations of distant galaxies to reconstruct the evolution of the cosmic gas. So he has done seminal work on this subject, and he will give, I think, an observational overview of the subject. Marta will follow. Marta is, again, a very well-known theoretician. She has done very influential work on the formation mechanism of the first supermassive black hole, proposing different ways to originate the seeds that then grow to very large masses. And then she has also done very influential work about the coevolution of black holes with their hosts, both with analytic and numerical methods. So I would like to ask Roberto to start, and I would ask all the participants, except Roberto, to switch off their microphone and cameras. So please, Roberto, welcome.
Yeah. Can you see the screen? I didn't hear anything, but I assume you can see it. So it's a pleasure to be here. Good afternoon, everybody. So the topic for today is high redshift quasars and how massive can the black hole be. And as anticipated, this will be a very observational heavy perspective in opposition to what Marta will probably present later. So just to set a little of context, we are talking about the cosmic dawn. We are talking about the first giga-year of the universe. Here, put just a timeline from the Big Bang till nowadays, till a giga-year after the Big Bang, and the redshift is kind of approximate. Numbers might change a little according to your preferred value of H0 and details, but basically we are talking about up to from redshift 5.6 to redshift 15 or so. And we can imagine to divide this area into parts. One that is in this pleasant and reassuring green, that's obviously the land of observations, and the spooky part is where the theory, we need to rely on the theory. And of course, the spooky, dark, and obscure as the champion Marta. Unfortunately for all the observers in the audience, you're stuck with me as your champion. So let's start with some basic facts. So first of all, there are a lot of quasars out there at this redshift. This is a plot that I've already shown, I think, at the AGN 13 conference, or a similar plot.
Yeah, no, slides are not showing up.
Sorry. Can you see? Now you see yourself, right?
You see, yes.
Do you see the slides now?
Yes.
Okay.
Now it works. Thanks.
Well, okay. So this was my 2-frame plot. We have observation and theory, and say that we have the 2 champions of today. Then unfortunately you're stuck with me. So this is the plot I was showing, I think, a couple of years ago at the AGN 13, maybe just slightly updated, and it summarizes a little what is the picture now in terms of what is existing in terms of quasars. I mean, what is known. You can see that the advent of large area, where large means over 1,000 square degrees, surveys in the optical and near infrared really changed the field. We have now more than 300 quasars known, redshift larger than 5.5, and you can really appreciate how quickly the field is evolving if you plot this in linear scales, and you see this really dramatic change of the picture in the last few years. The quasars I will be talking about are really bright. These are this plot shows the rest frame UV luminosity compared to the redshift for the high redshift end of the observed quasars, and you can tell that these are several orders of magnitude brighter than the typical galaxy. I think typical galaxies have the knee of the luminosity function for normal galaxies is somewhere below -21 in this scale. So we are a factor 100 or even more brighter than that. Of course, this is not the totality of the AGN population of this redshift. These are obviously the brightest sources that are the easier one to detect, and this is why we study them first. The second basic fact that I really need to stress here is that as far as we can observe them, even at the highest redshift, quasars are really self-similar. This is a very famous plot that I think all of you, most of you in the audience have already seen. This is taken from the Marta et al. Discovery paper of the first quasar found at redshift larger than 7. And the black histogram is the actual observed spectrum of that quasar, and the red one is a composite of Sloan spectra of quasars at redshift 2 or so. And you can tell that the composite is an incredibly well matched to the observed spectrum. So basically, from the first billion year until the next 10 billion years or so, quasars didn't evolve that much. That is telling us that quasars evolved extremely fast. But also it means that as far as we can tell, there's no reason to believe that we shouldn't be applying for instance, the black hole mass recipes that we use in the intermediate and lower redshift universe. So just as a reminder, how do we get black hole masses for these quasars? The classical argument is to use what is typically called the virial product. So you basically balance the gravitational energy of the clouds in the Bologna region with the kinetical energy, and you get constraint on the mass of the black hole. That basically depends on the velocity of the clouds squared, on the radius of the Bologna region, and some geometrical factor f. So, well, that's simple. For the velocity, we just measure how broad are the emission lines. This is an example from a recent paper from Shoei Fan and collaborators. This is a quasar redshift 6.5, and you can see there's the magnesium line here, and you can easily measure the width of the line, and you get the velocity. For the radius, it's a little more complicated, but not critically different. So the idea is that we measure the luminosity of the rest frame UV continuum, and reverberation mapping studies show that the luminosity of the UV continuum correlates with the size of the Bologna region, which in this plot from a recent paper by Dalla Bontà and collaborators, it's quantified as the time delay at which the Bologna region reacts to luminosity variation in the continuum of the AGN. So there is this nice correlation that basically allows us to simply use the luminosity of the AGN as a proxy for the size of the Bologna region. So we have the two basic elements. The third factor is a factor that is accounting for geometrical details and other nuance factors. and it's the order of unity. So with these recipes, this is the current picture. This is each point is a different quasar, and with the black hole measured in this redshift interval, you can see that we are talking about black holes that have some 10 to the 8 to up to 10 to the 10 solar masses in their black hole. So what is the problem? Well, the problem is obviously that if you assume that the black holes grew at the Eddington limit, so you can define a saltpeter time, that's the E-folding time, and basically for a given radiative efficiency, that's this parameter epsilon, and for the accretion rate, you get, if you assume that it's accreting at Eddington, you get a time scale is 45 million years. And why is that a problem? Well, 45 million years is short, but it's not really short when you compare to the age of the universe at this time. So if you take the highest redshift quasars known so far, it's around 700 mega years after the Big Bang. And that means you have about 6.8 decks. You have about 15 saltpeter times, so you can grow the black hole at Eddington only by a little short of 7 order of magnitude. So if the black hole is 10 to the 9, it means that it has to start at about 100 masses, solar masses at the Big Bang. And of course, this is extreme. Quasars don't start, the black holes don't start to form immediately at the Big Bang. You probably want some structure to actually form, some proto-galaxies to form. So let's say you start count at 250 mega years, that's about redshift 15, and then you only have a little more than 4 decks to that you can allow to grow the black hole. So if you take, for instance, the most massive black hole in high redshift quasars known so far, it's a little above 10 to the 10 using our recipes. And you trace back where was it, if you assume that it's creating at Eddington throughout its history. The nice thing of plotting everything in log versus time is that this is a linear growth in this scale. So you can easily see where this is going, right? At redshift 15, the seed has to be around 1,000 solar masses per year. Even more so, you can tell if you push in redshift, even with a black hole that is not as extreme. So Pisco, the redshift 7.5 quasar that I'm lighting here, as a black hole of close to 10 to the 9 solar masses. And you trace it back, assuming it's creating at Eddington and everything, and by redshift 15, the seed has to be order of close to 10 to the 5 solar masses. So here's the problem. We need to explain these massive quasars for assuming that they're growing simply at Eddington limits. You really need massive seeds. So the possible scenarios, you have heavy seeds, as I just said, or you play around with the parameters that enter the definition of the saltpeter the saltpeter time that I showed here again. So you can either increase the Eddington, the accretion rate, so you push it above Eddington, or you can decrease the radiative efficiency, and the result of both these operations is that you reduce the saltpeter time, so you can basically squeeze in more E-folding in the short time span of the universe. The third option, obviously, is that the masses we are getting for these massive black holes in these extreme quasars are wrong. And I like to order in this way because basically the first point attacks the starting point of the evolution, the second point attacks the evolution itself, and the third point attacks the final point of the evolution. Of course, as you saw from the previous plots, basically everything that has to do with the first 2 points is in the dark land of theory, which I will leave happily to Marta. And I will only mostly talking only about the last point. How can the massive black hole, can the masses of this black hole be wrong? So I will go back to this slide that I showed before, and let's go step by step, right? So it's possible is it possible that we get the velocities wrong? This used to be a problem, especially in the early days, and in some cases it's still the case. Of course, in my introductory slide, I showed a beautiful spectrum with perfectly detected emission line. In many other cases, we're not as lucky. This is an example, and I promise this was the worst spectrum I could find from the very recent literature. But sometimes we have to fight against very poor signal to noise, and of course, in these cases, it might be that we are getting the measure wrong. Now, signal to noise is I would argue is no longer a main limitation. Some beautiful data sets are getting observed, and I think probably the pinnacle, the state of the art is captured by this nice image that shows a compilation of Redshift 6 and beyond quasars from the XQR30 program. This is an X-shooter, a large program led by Valentina Dodorico, and these are actual spectra. You can really appreciate the quality of the data here, and you can. I would argue there is no denial that signal to noise is no longer a limit for this kind of studies. We get very good measurements of the line profiles, as good as it gets. So if it's not the line, another option could be the measurement of the radius of the Broadline region. Certainly, a big caveat here is that the relation that we use to pass through from the luminosity to size of the Broadline region has a scatter. I try to highlight it here with this shaded area, and the scatter is not small. We're talking about up to 0.5x in the scatter, and that affects all the masses of black holes that you get with these methods. It's bad, and it means that for an individual quasar, you shouldn't rely on the value of the mass within a factor of 3 or so. On the other hand, this is not a systematic effect. On average, we get it correct. And if you look at the scale on the x-axis, there are now even very bright quasars that are observed in reverberation mapping campaigns. So even the regime that we are now probing with the quasars at redshift 6 and 7, it's not really different in terms of parameter space to what has been studied in reverberation mapping. So we can be fairly happy with the kind of relationship that has been observed so far, and I think there's no reason to believe there's a significant deviation. Could it be that the geometrical factor is the problem? This is a big problem on individual cases. You can imagine if the Broadline region is mostly a disk, and then you have the inverse of a sinus entering the equation. This F factor will be something like 1 over the sine of the inclination angle, and then the correction might change a lot from object to object. And of course, the inclination angle is something that is basically unconstrained for these quasars. On the other hand, again, this can be averaged out. If you observe multiple sources, you will get random orientations, and this should be cancelled out. The average value is calibrated in lower redshift samples, where you have different handles on, like comparing with host galaxies, or different in local samples. You can even do the direct reverberation mapping measure of the black hole mass. So there are ways to calibrate this out, so on average, this should be fine. So could it be that the whole starting assumption is wrong? For instance, if the virial product does not apply. This is obviously a very good point. This, for instance, was there was a paper a few years ago by Alessandro, Marconi and collaborators, where they suggested that radiation pressure can be important. This was not applied for high-ratio quasar, it was for narrow line separate ones, but the argument stands. If you have a significant contribution of radiation pressure, that might alter the estimates of the black hole mass. But in which way? Well, what happens is that if you have radiation pressure, basically this would yield even higher black hole masses than what we are using. So the problem applied to redshift 6 and beyond quasar will get even worse. Also, in the local universe, this recipe for the virial product has been tested in individual sources. The obvious example I can tell is NGC 5548, which is the most studied type 1 AGN with all the reverberation mapping campaign, and they see that when the luminosity of the AGN is lower, the velocity is larger, so that compensates, so they get the same black hole mass. So it seems like the virial argument works, at least for lower luminosity AGN. And again, we don't have a strong argument to go beyond that. But even if you want to question that, right, you can just assume that all these quasars are accreting at Eddington, and you get the same masses. This is captured by this plot. So using black hole masses that we get from the virial product, and comparing them with the luminosities we observe, we get the typical redshift 6 quasar, which are all these points, the black and the colored points, are all accreting basically at their Eddington limit. For comparison, the gray points here are a quasar sample from Sloan. So you can simply ignore everything you know about all the spectroscopy, take a UV continuum measurement, assume the black hole is accreting at Eddington, and you get the mass basically right to the first order for these very high ratio quasars. Of course, if you want to respect the Eddington limit and assume lower Eddington rate, then you get again a bigger black hole mass. So the problem of the black hole masses becomes worse. So in conclusion, the masses, you shouldn't trust the mass of an individual quasar to more than a factor of 3 or so. And then this applies to most redshifts, but on average, the masses we're getting are fine. There's no reason to believe they're massively wrong. I will go through a few outlook scenarios that we are trying to just to show a few different paths that we're trying in order to get independent measurements of the black hole masses. And one is that if you model how the accretion is going on the quasars, you can have a different prediction for the quasar SED, in particular for the optical and UV rest frame optical UV emission. The different SEDs might carry information on both the black hole mass and the Eddington accretion. This is a work that I'm doing with Tullio Sbarrato, Massimo Dotti, and others, where we are trying to take advantage of these models, convolve them with some observational limitation. For instance, the fact that we have different viewing angles, some reddening, you have the Gunn-Peterson effect, then you fold everything against the throughput curves of your favorite photometric system, and you get a predicted SED of the quasar that you can compare with the observations. And then with this, you can get constraints again on the black hole mass and on the Eddington ratio that are independent from any spectroscopy at this stage. Another way forward is to take advantage of the very high resolution observation of the cold gas in the host galaxy. In these images here, I'm showing the maps of the dust here and of the C+ line in a quasar redshift 6.6. And the amazing thing here is the angular resolution of this observation. We get a full width of less than 0.1 arcsecond, and that's 400 parsec at the redshift of this quasar. It's interesting because for a black hole of 10 to the 9, and if you assume that the dispersion, the gravitational potential is traced with a sigma of, like, say, well, a width of 300 kilometers per second, you get an influence radius of a few hundred parsecs, right? So these numbers start to be extremely comparable, right? So it's tempting with this data set, or even with pushing even further the resolution, it's tempting to try to see if we get a look at the dynamic of the gas within the sphere of influence of the black hole, which would give us a direct measurement of the black hole mass. Unfortunately, in this case, you can already tell from the bottom right panel here, there's no obvious spike in the velocity dispersion in the central pixel where the black hole is. You see only a marginal increase here in the velocity dispersion, but that's reflected by it's matching the part of the velocity field where you have a sharper contrast, and that's basically what people refer to as the beam smearing effect. And you can appreciate this if you extract the position velocity diagram. So this is the velocity of the gas along the major axis of this system, and you see that in the central pixel you don't see any spike associated with the larger velocity dispersion that would be suggestive that the black hole is dominating the gravity there. And the reason here, the problem is not technical. It's not like we lack angular resolution. The problem is of astrophysical nature. If you look at the C+ map and you compute the luminosity in the central beam, you get that the mass in ionized carbon is a few times 10 to the 6. This is a pretty robust estimate based on first principles, assuming that the C+ emission is optically thin. And if you convert this into a molecular gas mass, assuming some abundance of carbon over H2, you get a mass of the order of 10 to the 10. And here's the problem. This is already 10, 11 times larger than the mass of the black hole for this specific quasar. So in the central resolution element, there is so much gas that this is dominating the dynamics even more than the quasar. Of course, a way to even further...
Excuse me, Roberto, it's, I think you have only a few minutes more.
I'm closing. The other option, of course, is to get as many quasars as possible and even the highest redshift. And the problem in this case, obviously, is that it's increasingly difficult, right? In this plot, I'm showing the prediction for the dark matter halos mass functions at various redshifts. And you see for a typical halo of, say, 3 times 10 to the 12, you see that from redshift 6 to redshift 9, you drop by more than 3 orders of magnitude. So it's these objects become rarer and rarer. So it will be extremely difficult to find them. And I think that's everything I had to say, and I yield my time.
Yeah, thank you very much for this overview on the black hole mass measurement problem. And as I said, we can postpone the question at the end. And so I would invite Marta to start the presentation.
Hello, everyone. Can you see my presentation?
Yes.
Okay, awesome. Good. So now I will return the favor to my fellow knight by discussing with you the theory, or, well, let me say it a different way. I'm actually going to address literally this question. How massive can black holes be at this high redshift? Can we make black holes that are even more massive than what we see today? So let me start. So, Roberto showed you many observational pictures, and being a theorist, mostly have equations and boring plots, but I will start with the movie. This is a simulation, a very high resolution simulation showing the formation of a high redshift black hole with a mass similar to that of Pisco at redshift 7.5. On the left, you see gas, and on the right, you see stars. This is mostly to give you an idea of what type of environment we're talking about when we talk about high redshift quasars. It's a very lively environment, and these are galaxies that are very, very massive. At redshift 6. So the black holes are massive themselves, but the galaxies as well. And again, they go through a lot in their short life. So keep in mind this sort of picture. And now we can go through a few ways to make these very massive black holes. So let me start with something that Roberto has already said, but just shown in a slightly different way. So again, here I have a figure showing black hole mass as a function of redshift. These are some observed quasars. This is from a few years ago, but I like this picture because it shows not only what happens when black holes accrete at the Eddington rate, but also when black holes accrete at less the Eddington rate. So let me recast the same equation that Roberto had, but now let me add an extra parameter here, which is the Eddington ratio. So the maximum, so if we assume the Eddington limit, the maximum value for this f-add parameter would be 1. But in principle, you can have also a lower value. And in fact, you see here that the growth time, so that there is a degeneracy in practice between the various parameters. So in some sense, you can think of accreting at the Eddington rate for a given amount of time, or accreting at half of the Eddington rate for double the amount of time. And this is the way I prefer to phrase this question. But so in general, if you assume that you measure a black hole mass at a given redshift, and you know the age of the universe at that redshift, then you have three parameters: this Eddington ratio, the relative efficiency, and the initial mass of the black hole to play with. So in this figure, I played with these three numbers to make a 10 to the 10 solar masses black hole. For instance, redshift 7. So let's look to the future. Let's see if we can find a 10 to the 10 solar mass black hole at redshift 7. If we find this object and we assume this type of physics, then we can use this figure to estimate the combination of parameters that can give us this growth. So for instance, if we start with a seed of say 10 to the 4 solar masses, then this seed must have grown from the beginning of the universe at 90% the Eddington ratio for the whole time, or from 90% of the age of the universe at 100% Eddington. So this seems perhaps a bit difficult, not much because of the time when the seeds form, I will go back to this, but because it's not very easy for black holes to grow in small galaxies. So what several theoretical groups are finding is that in low mass galaxies up to a mass of 10 to a 9, 10 to a 10, black hole growth is not very rapid. So in this figure of black hole mass versus stellar mass, you see here, this is the same simulation that I showed you earlier, just in a different, in a more quantitative way. So this is a redshift 7 quasar, and you see that until the galaxy reaches about 10 to a 10 solar masses, the growth of black hole is very slow. Only after this, it starts with a rapid growth, basically at the identical rate. So this means that, as the initial galaxy grows, the black holes don't grow at the same pace. So this 90% of the age of the universe becomes a bit complex to fulfill. So what can we do at this point? So I will go through a few hypotheses that have been suggested over the years, and I will conclude with my favorite two. But basically, what we can do is, for instance, the simplest approach is to change the parameters in our equation. So I told you that the three parameters are the initial mass of the SID, the relative efficiency, and this minimum Eddington ratio that you have to use. Now, I use an epsilon of 10%. Roberto did pretty much the same, but that's not a fixed value. How about we take an epsilon of 0.05, 5%? Wow, now things change dramatically. So for the same black hole of 10 to 10 solar masses, now it takes about 40%, an Eddington ratio of 40% to grow from a SID mass of 10 to 4 solar masses. This is quite remarkable, isn't it? You just change a little small number and you get a lot of bang for your buck. So why not changing this relative efficiency epsilon? Well, it's not a totally free parameter. The relative efficiency, at least for a thin disk, a Shakura-Sonnet disk, depends on the spin of black holes. So here you see this relative efficiency, a function of spin. This is the value of the spin, high spin. Then as the spin decreases, the relative efficiency decreases. And then here you see that the absolute value of the spin increases again, but with a negative value. This is a case when the accretion disk rotates in the opposite direction with respect to the rotation axis of the black hole. So these little arrows show basically angular momentum vectors. And so you see here that if you have a slowly spinning black hole, or a black hole that doesn't spin at all, or a counter-rotating disk, you can get very low values, 5% or so. And this gives you a lot of growth for your black hole. Is it, as easy as that? So this was proposed by King and Pringle in 2006. They suggested that if you feed black holes with very short episodes of accretion, they called it chaotic accretion, that you can keep black hole spin low. And if you keep black hole spin low, then you have about 6%, no problem at all. However, there is a small caveat, which is that it's not that to have this chaotic accretion to be really effective in keeping the spin of the black hole to zero, then you need basically a very, very isotropic distribution of gas. If you have even just a little bit of anisotropy or a little bit of angular momentum in preferential direction, you end up spinning black holes up. And so you go back to the same problem. So this is, just changing the parameter in the equation. Can we think something even more exotic, more difficult? Well, who called the Eddington limit a limit? This is something that I always find bizarre, at least after working on the Eddington accretion. We call it a limit, but it's not really a limit. Technically, the Eddington limit just describes the situation in which, in spherical symmetry, the outward radiation pressure equals the inward gravitational force. So simple radiation pushes away the gas, and the black hole cannot accrete anymore because no gas is reaching the black hole. In reality, black holes are not usually fed in spherical symmetry. They are accretion disks. So we have to take this into account, and the Eddington limit just becomes the Eddington ratio because there have been at this point decades of study that show that super-Eddington accretion disks can be stable. Here, this is a short summary by Tchaikovsky et al. In 2015, showing accretion disks from low accretion rate, low Eddington ratios, to very high Eddington ratios above Eddington. And also, we observe super-Eddington accretion in TAL disruption events. So this is not so crazy after all. What are the specifics of this Eddington accretion? So first, accreting at super-Eddington rates does not imply that you have super-Eddington luminosities. Some of the quasars that we have observed, at least there was one case that would perhaps is super-Eddington, but does not have enormous luminosities. The reason is that when you have accretion disks that are fed at a very high rate, you have very high densities, and then they become basically optically thick. So the photons that are produced in the disk are not able to escape the disk itself. And they're actually accreted inwards and they're vectored into the black hole. So the photons simply don't leave the disk, so they don't produce light. And so the luminosity is suppressed, and it's around the Eddington value. You can think of it, again, as a way to lower the radio efficiency that we had in the previous equation. Although it's a bit more complex, but this is a simple way of thinking about it.
It's wrong.
Hello? Hello? Someone is... I will continue unless...
Yeah, please go on.
Okay. Is this as easy as this? Well, also in this case, there are a few caveats. So they said you can think of the luminosity being suppressed, but it's unclear how small the relative efficiency can actually be. So this is a figure where I compiled several results from simulations and analytical models. This is the luminosity in units of Eddington luminosities as a function of the accretion rate onto the black hole, again in Eddington units. Each of the dots is a simulation, GRMHD, relativistic magnetohydrodynamical simulation. Some of them have radiation as well. And the color differs depending on the spin of the black holes. Now, these dashed lines would show show this ratio if the relative efficiency was exactly the same as we have in a relatively efficient accretion disk. So it depends on spin, and the luminosity will be linearly dependent on the accretion rate. These solid lines are taken from a paper by Madao et al., in which they take into account this trapping radiation and use results from some simulations, I think, by Sadowski a few years ago. But then if you look here, the results of the simulations are all over the place. And some of them, like these triangles here, are super Eddington, clearly, but they're not relatively suppressed at all. The luminosity is as close as what you would expect from just luminosity is proportional to the standard relative efficiency. So this is the first caveat. The second is that although in super-Eddington accretion, radiation may be trapped, you always find in all the simulations the production of very powerful jets. Powerful and probably heavy jets that are able to push away the gas from around the black hole, around the bonding radius. And so this may imply a very short duty cycle for super-Eddington accretion. But again, this super-Eddington is the Eddington limit is not a limit, and this may happen as we see it happen in other disruption events. Now let's move on to a third option. Well, if growing black holes by accretion is so hard, how about we just merge black holes? We have many black hole mergers, and we get a lot of mass without having any problem with that radiation. So let's try this. This is actually a very good suggestion because, as Roberto showed in one of his slides, you expect these high-redshift quasars, these very massive black holes, to be hosted in high-mass halos. These are biased regions, and in biased regions, you have many, many more halo mergers and galaxy mergers. So if most galaxies host massive black holes, then you will have an enhanced black hole merger rate. If you look at this figure, which is taken from the LISA Science case in 2013, look at the yellow and violet black holes. This shows the evolution, the mass growth from high redshift to redshift about 6 of two black holes that have masses about 10 to the 8 solar masses at redshift 6. And you see here all these white circles. Each of these represents a black hole merger. So if you compare this to a black hole just like the Milky Way's black hole today, you see that there are there are much fewer black hole mergers in a normal black hole rather than in one of these high-redshift quasars. So we do expect that there are lots of black hole mergers taking place near or around or on the black hole that will form a high-redshift quasar, redshift 6 or higher quasar. Is this as easy as that, as I just described? Well, also in this case, we have a few caveats. One is the so-called gravitational wave recoil that can eject black holes. When two black holes merge, they emit gravitational waves. Gravitational waves carry energy, but they also carry linear momentum. So just by conservation of linear momentum, the merging black holes, so the merger remnants, will recoil in the opposite direction with a velocity that could be very high, up to thousands of kilometers per second, but on average is about 100 kilometers per second, which is not a super high value today. It's about the velocity dispersion of the Milky Way, but it's higher than the escape speed from high-redshift galaxies. And so basically you have merging black holes that are, as the moment they merge, are ejected from galaxies, and so you go back to square one. And of course, black hole merger timescales are also highly uncertain because, well, it's already a complex physical problem, but also high-redshift galaxies sometimes defy our analytical expectations. I showed you in the movie how crazy these galaxies were mergers at all times, and I think that could be another turn, trying to describe with a simple analytical potential a galaxy of that shape and that times. So this brings me to option number 4, which is start big already. I mean, if I start with a super duper massive black hole already, why is that a problem? Can't I start with that? Well, this is actually one of my favorite options. So here I summarize some of the what we know about black holes. This is shown with the yellow and purple mass functions. This is about from a figure by Monica Colpi, where we see stellar black holes and supermassive black holes all the way to these monsters up to high redshift. And then I put here some models, theoretical models to form black holes. So we want to start big. If we want to start big, say 10 to the 4 to 10 to the 5 solar masses, basically we're left with gas-driven dark collapsed black holes, primordial black holes, and wow, cosmic string loops. Look at these masses, 10 to the 8 to 10 to the 10. Now, in these models, these are based on stars and gas. The location in this plot gives an idea of the relative number. But from primordial black holes and cosmic string loops, I put these arrows in. The mass axis is okay, but the number density is completely unknown. So dark collapsed black holes that are the most massive among these solutions, these possible formation mechanisms that I highlighted in the previous slide, can be as massive as 10 to the 5 solar masses, perhaps, but they're relatively rare. So we don't know if you form enough And if you form them exactly where they should be to become a high-redshift quasar, although high-mass halos at high-redshift are favored. This was work done by Rosa Valiante, and I suggest that you talk with her because she's the real expert here. But the main point is that dark cloud black holes are a bit rare. They may work, but we are not sure. And also high-redshift galaxies, I already said this, are really massive. Black holes are not always sitting at the center of galaxies. So not only you have supernova feedback destroying their gas supply, you also have shallow potential wells where the black holes could be anywhere in the galaxy. You know, when we think of black holes like in the Milky Way, you know that the black hole is right in the middle of the center of mass. But this is not the case if the galaxy is not a really, really good center of mass. So black holes that are, you know, jittering and moving around galaxies have a very hard time growing. So this comes my favorite solution: primordial black holes and cosmic string loops. Now this has several advantages. So first, black holes form as early as at inflation, before galaxies. So when Roberto earlier on said, "Oh well, black holes don't form at the Big Bang," well, some can. So you really have the whole time to grow. Not only, but the best thing, in my opinion, is that the galaxy grows around the black hole. So at this point, you're, you know, after inflation, you have the small inhomogeneities of, you know, in the standard lambda CDM model, these small inhomogeneities will attract more and more matter by gravity, and so that's how you form dark matter halos. And then these dark matter halos will attract baryons gas, which falls in and then forms stars. But if you have on top of this, you know, the standard lambda CDM distribution, some primordial SIDS, primordial black holes, formed again as primordial black holes or as cosmic string loops, then you have some overdensities that will attract more and more matter. So in this case, the point is the galaxy grows around the black hole. And so you solve a lot of the problems that you have in standard models. You don't have to try and put the black hole at the center of mass of the galaxy, because the galaxy grows around the black hole, which is the center of mass. And also you can start growing even before star formation. And so this, you know, kind of solves the issue of the supernova feedback. What is the caveat? Well, we don't know if they actually exist or they're really formed. So this is a very cool proposal. This has been, you know, kind of proposed very recently in the literature, but it's pretty cool. So I will leave you here with really my favorite one, which is the black hole theory. Just boom, black hole here. And thank you.
Okay, thank you very much, Marta, for this very nice overview of all models of black hole formation. I don't know what is the favorite of the people in the audience. I will start asking whether there is anyone who has a question, either for Roberto or for Marta. And if you have it, please book it on the chat so we can keep the order of the questions. And if nobody starts, let me start then. It's actually a question for both, probably. Probably is also a question that is recurrent in this field. And suppose supereditor accretion is common. Many of them, these objects are accreting at supereditor rates with the high-redshift universe. How do we know that observationally, besides seeing luminosities that are slightly above the Eddington? Is there any way observationally from either optical spectrum, the X-ray spectrum, to tell that supereditor accretion is occurring?
Observer, please start.
Well, it's a good question in the sense that I believe nowhere at any redshift, even the brightest quasars, redshift 2 or so, there is no object that stands way above Eddington, right? So all the informations we have objects that are above the Eddington limit, but we don't have the clear case that we can test against, right? That we don't have the obvious object that accretes 100 times Eddington, and that we can test if where we can test if the empirical recipes we're using are still make still sense. From what I've presented, right, we don't have arguments to say that the measurements are wrong by a lot so far. Of course, maybe one way to test if there's if we find more prominent variability, for instance, in quasar that are potentially accreting at higher ratios than the Eddington limit. That might be a hint, but I think as far as we can go is just measuring the period products as well as we can, and that's it. Marta, do you have suggestions?
Well, from the theoretical point of view, I have to say that we expect that super Eddington growth would be more common in the earlier phases when the black holes are not very massive, simply because you have a 10 to 6 solar mass per hole, with 1 solar mass per year of gas would be highly super Eddington. While being super Eddington for a 10 to 9 solar mass per hole, you need a lot of gas. So I think that Roberto showed some recent work by Chris Dunn on the spectra, with 2 ways of testing this. But yeah, there are 2 additional points. One is that with super Eddington, you expect always the formation of jets. Know that radio jets at higher altitudes are difficult, but perhaps hard X-ray can help, and I will, Gabriella gives a video perhaps can be helpful here. And the other is that probably if you are creating at very, very high rates, you will have a very high nuclear obscuration. Just if you calculate the column density to have an accretion rate that is super Eddington at, let's say, 10 to the 8 solar mass per hole, column density to have near black hole is very high. So this makes observations a bit more complex, I think.
We can move a bit. The problem, if it's obscured, then it's really hard to find them, right? So there's a reason why basically everything we know is type 1 at this redshift, I'm saying. It would be very nice to have a census of the obscured fraction at this redshift. It's extremely painful because the type 1 are like, at these luminosities, we're talking about 1 quasar every 60 square degrees or so, 100. So it's hard. Even if you have 10 times more unobscured sources, they're still pretty rare.
We'll get there, hopefully. So,
yes.
Sorry, I think I overlooked the chat, and I now see, starting from Roberto Maiolino, there are a series of questions. So, Roberto, another one.
Yeah. Well, the first question was for Marta about super Eddington accretion, but it's been already discussed widely, so I will skip that. I will therefore focus on the question for Roberto. And about the measurement, the reliability of the measurement of the black hole masses at high redshift, I fully agree that it's not a matter of signal to noise because some of the spectra are really gorgeous. But they are all based on the magnesium too, which lies in a spectral region which is really hopeful in terms of purity because it's embedded in this pseudo-continuum, bumpy pseudo-continuum of the iron lines. So it may well be that it's difficult to disentangle the proper line, magnesium 2 line from the iron 2 forest. So I think the sort of a more solid assessment of the black hole masses can only really come from H beta or H alpha, which can only unfortunately be measured with GWST but the deadline for, the proposal deadline is in a few weeks, so hopefully we will have some better assessment in 1 year or so. I don't know if
No, I totally agree. I'm not sure if there was a question in that. I would reply with a counter question.
Yeah.
Do you think that the black hole, the width of the line, which is basically the parameter you get from magnesium, would be so off? I totally agree with the premise, and I totally agree that we should take H alpha spectra to at least to make sure that we are not off. But if you have to speculate, would you expect a big difference, or?
I mean, it could be because our current fitting is based on low redshift templates of the ion continuum, and who knows what the hell is happening at these early times. And so if everything behaves similarly, of course, maybe the effect is not major, but if things change at some point, it's significant, so hard to say.
Yeah.
So thanks, Roberto. Let's move to the next question by Andrea. Andrea, please.
Yes, Marta, the question is quite simple. Is there a limit of this primordial black hole, on the mass of this primordial black hole? Because when I was studying the black holes from inflation ages ago, I remember that you could produce these mini black holes that will eventually evaporate with the Hawking mechanisms, and that was the bulk of the discussion and about this primordial black hole. So I don't know. Maybe there is no reason to have a limiting mass, but just wonder.
Okay, so the mass, so for primordial black holes, not cosmic string loops, the mass of the black hole is the mass of the horizon at the time of formation of the black hole. So the time of formation has to be, let's say, most during the radiation era. So you expect at most 10^5 solar masses or so, 10^6. There is a recent paper by Bernard Carr on stupendously large black holes. That goes up to 10^10, really. But the main point, so the reason why generally all these high masses are ruled out is that you cannot have many of them. In other words, you have strong bounds on the product of mass times the number density. In other words, the omega parameter, the mass density parameter for these objects. So at the moment, there is a recent paper that does this really, really nicely. It's by Serpico et al., I think 2019 or 20, and shows that in principle you still have some room in which you can form massive SIDS and respect all these bounds, although it's a bit fine-tuned. So most likely for primordial black holes, you would have to start with slightly lower masses. But in principle, the mass spectrum can extend. I mean, in principle, in theory, can extend up to very large masses. But the number density must be very, very small.
Okay, thanks.
Thanks, Marta. Now there's a question from Bozena.
It's about this formation of the seeds which you favored. If we have an independent mechanism like strings, whatever, and then the galaxy forms around, then I would expect a large spread in metallicity of the observed quasars, because then you would sample the whole stage of the galaxy evolution around. On the other hand, I think we do not see that much of a spread. We do not see pure hydrogen quasars, which might rather imply a very closely connected evolution, at least of the innermost part of the galaxy and quasar activity.
So first, when I said that it was my favorite, well, I really like it a lot. But this was part of the Tourney kind of jokey attitude. I don't have a favorite mechanism. I mean, as I said, my favorite one is the black hole theory, but I don't think that's the right one. But going more to the science, I mean, in principle, if you think of these primordial black holes or cosmic neutron loops, there is not much difference compared to the standard evolution, except that you have a massive black hole in the center. So you would have star formation and everything else, like in all the other cases. It would probably actually start earlier. So in principle, if I were to predict, I would expect a higher metallicity rather than lower. Because since you create you kickstart the evolution of the dark matter halo, and you give it a stronger gravity field, then it should be easier to accumulate baryons. But this is totally, thinking on top of my head right now. Unfortunately, this is at the moment, this is a very theoretical argument, and there has been no full development of these type of proposals. Carr and Silk a couple of years ago, I think 18, and Bramberger 15 were the first two papers that proposed this. Now there is a lot of talking about it, but there is no specific quantitative prediction that I know of.
Yeah, okay, thank you.
Okay, thanks. So there's a question by Alex raising. So Alex, do you want to make your question?
Yes, hi. Probably a question to Roberto. Basically, there has been an article very recently about discovery of a galaxy, I believe in Boss catalog, that appears to be very bright, quasar-like bright, but not because of the accretion to the black hole, but because of star formation, super active star formation. So my question is whether current quality of spectroscopic observation allows us to distinguish between these two mechanisms of super brightness for high redshift quasars, and do we know some quasars that are actually not that bright because of accretion, but because of star formation?
So it's a very, very good question. I haven't studied. I'm aware of the paper we're talking about. I'm not. I don't remember the details very well, but I think the point that there is no evidence in that source that there is broad emission lines, which seem to be very common in all the quasars we observe, with the traditional quasars I've been talking about. Now, all the quasars that we've observed at this redshift are hosted in galaxies that form hundreds and sometimes even thousands solar masses per year. So all these galaxies are forming stars at huge rates. That said, we see a lot of dust emission, 10 to the 7, 10 to the 8 solar masses in dust, which means that these objects are chemically enriched already. As far as we can tell, the metallicities are probably not very far from solar, it's hard to imagine you have such a huge star formation rate as traced by the dust, and have it at similar level in unobscured star formation that you see in the Restream UV. Typically, what we see anywhere else in the universe, we see that when you have star formation rates that are so high, the fraction of infrared to UV increases a lot. Basically, most of the emission becomes enshrouded in dust. There might be occasional cases like the source that we've been discussing, which still is a factor 10 lower in luminosity than the quasars have been discussing, but this might be more the exception than the rule. I think it's very difficult to explain the luminosity we see in the spectra. We don't have reasons to believe that the quasars, most of the quasars we consider are bona fide quasars. There is a a gray area maybe in the lower luminosity region, and especially a lot of the sources that have been selected with the Subaru efforts, which goes much deeper in a smaller area of the sky than what I was referring for the slow and kind of survey. Those quasars have luminosities of -23, -24, which are at the limit of very bright galaxies. So you can have the occasional bright galaxy. At some point, the luminosity function of quasars and the luminosity function of galaxies in the UV interact, and then they overlap, right? And you might get the occasional very bright galaxy that looks like a quasar. And in some sources, it might be difficult to define the boundary, but I think most of the quasars I've been talking about are way too bright for galaxies.
Okay, thank you.
Thanks. I do not see any more questions on the chat, so maybe we can close this session and thank the speakers and the participants. Paolo, do you want to make a final remark?
Yes, I mean, thanks to the Knights, Marta and Roberto, thanks to the chair. And so we will reconvene tomorrow at 3 p.m. As you know, there will be Margherita Giustini and Francesco Shankar, chaired by Paola Marziani, talking about creating AGNs, triggering Super Eddington, and more. So I would say that thanks for being here. I think we had more than 130 people, and I hope you enjoyed the talks. Thanks a lot again to Marta and Roberto, and da Firenze è tutto.
Thanks a lot for this.
Thank you.
Thank you. Bye-bye.
Bye.
Bye-bye.
Yeah.